And then I can go ahead and begin. Okay, so looks like the recording has started. So I wanted to start again with a few general announcements. So first off, this week in lab, we'll be having midterm number 2. So do make sure that you attend your lab section. We'll be doing exam during that period. The main focus for exam 2 will be our combustion problems and psychometrics. So those are the things that we've covered since exam number 1. However, I want to remind everyone that psychometrics, combustion, both have built on the idea of gas mixtures. And so it's not like we're not going to see some of the content from exam 1, but basically it's now built in to some of the other material that we've seen since. And so I just want to remind everyone, again, psychometrics, combustion are the main topics, but gas mixtures are still things that you need to know. It's not the main focus, but again, it came in because it's an underlying kind of prerequisite for our 2 topics. So that is the main focus. In terms of the exam, it'll be the exact same setup as the first exam. So you're going to be able to bring in your calculator, pen, pencil, preferably pencil, eraser, and then if you want anything to drink, you're welcome to bring that in. Otherwise, I will bring the exam document. I'll bring the lookup tables if you need them. I'll provide any extra information if you need that as well, and also have the printed equation sheet. So you're welcome to you don't have to print that out. I will be bringing all of that in, so you don't have to worry about that. So basically, same setup as before. If you do have any questions about the exam, let me know. I will try and answer them as best I can. Otherwise, I just wanted to remind everyone that there are some example problems that you can go ahead and work posted on Canvas. So do take a look at those. They're good review for both psychometrics and some of your combustion. So that would be the kind of review material that you'd want to take a look at. And so if you do need a psychometric chart for the exam, I will include that with either the problem or I will include it with the extra information that you'll be getting either with your, I call it your equation sheet or a lookup table. But if you need it, you'll have it. You don't have to bring your own psychometric chart for the exam. Okay. So again, if there's any questions, don't hesitate to ask. If you have any questions about working on the example problems or review problems, again, I will be willing to answer any questions that you have on those. I'll try and get back to you as soon as I can. But if you're working too late at night, I can't guarantee you the turnaround on the exam problems. Okay, or I should say the example problems. Otherwise, the last thing I wanted to note was that you do have homework due tonight. It is your combustion homework. So it's all of combustion from stoichiometric balances all the way up through this problem, which is going to be the adiabatic flame temperature. So again, just a reminder to work on that because that will prepare you also for the combustion portion of the exam. Okay. Otherwise, that was the main thing I wanted to cover. In terms of reminders. The rest of the time, we're going to be trying to finish up this example problem, and then we're going to do some concluding comments on combustion in the PowerPoint. So that is how we're going to spend the rest of today in class. And so since it was over the weekend, I wanted to kind of just review what we're doing here. What we're doing in this problem is we're looking at a octane gas. We are burning it with air with 30% excess air, and we are bringing in 60% relative humidity. So we had water coming into our system, and we were asked to calculate the adiabatic exit temperature of the gases. So that would be our adiabatic flame temperature. And so we're trying to find what is the maximum temperature of the product gases for this given configuration. So in terms of the setup, what we did last week on Friday, we did the stoichiometric balance. We were able to set everything up and account now for the additional water that's going to be in the system. So that additional water came through the combustion process. I'm just going to change how we did our stoichiometric balance. And we were able to use our basic terminology from gas mixtures to help us be able to figure out what is the amount of water that was in the system originally based on our humidity ratio. And so once we did that, we did all of the calculations, we found that value, we finished the stoichiometric balance. Once we had the stoichiometric balance, we were able to push forward into conservation of energy, where we said we had steady state, we had it adiabatic, and there was no work. And so the sum of all of our reactants has to equal the sum of all of the products. And we got to writing that entire term out, where we had to take into account all of the enthalpies that we had for both the product side and the reactant side. And what we were trying to set ourselves up to do was to be able to now solve for this green enthalpy term, because that green enthalpy term here, this is the enthalpy of the state at the product side. And that product side state is going to be a function of temperature. So we need to solve for the green enthalpies here in this equation. Now, to do that, we were able to make several simplifying assumptions. Because we brought it in at the standard state, the enthalpy at the state and the reference enthalpy for all of the reactants coming in went away. So that was this term here, this term here, this term here, and this term here. Those all ended up canceling out. And then furthermore, we knew that for oxygen and nitrogen, so we had a nitrogen here, that the enthalpy of formation is going to go to 0. And so we were able to eliminate those values just because we knew that the value went to 0. And so what we ended up doing is we said, okay, now we have this form. We want to set this up so we can now solve for the green H's. And so we want to leave the green H part on the left-hand side. Anything that is not green, we are going to move over on the, or that's on the product side. We're going to move it over to the reactant side, which means it's going to be on the right-hand side of this equation, because this equation loops around. And so what we're going to do is we're going to go ahead and do that. And what we're going to end up with is on the left-hand side, we're going to have the molar flow rate of the water coming out of the system. So it's going to be our product side. This is now going to be the enthalpy of the water at the state. And so we'll note that this is on the product side. Then we'll have the molar flow rate of the carbon dioxide, the enthalpy of the carbon dioxide at the product state. Then we have plus the molar flow rate of our nitrogen, N2, plus the enthalpy of nitrogen at the product state. Plus then we have the molar flow rate of oxygen and the molar enthalpy of oxygen at the product state. And so this represents the left-hand side. It's just these 4 green enthalpies. We've just kind of combined it into kind of this left-hand term. And on the right-hand side, we're going to go ahead and combine everything else. So in terms of the first thing, we have our fuel. So we'll have the molar flow rate of our fuel, C8H18. In terms of that, we only now have the enthalpy of formation for the fuel, C8H18. So that is the first term. Second term, we have oxygen coming in, but we said this entire term, the enthalpies all are going to cancel out, so we don't have to worry about anything in there. Third term, we have nitrogen. We said these 2 enthalpies cancel. This enthalpy of formation was 0, so we have no enthalpy term for nitrogen on the reactant side. And then we have just one last term, which is going to be from the water from our moist air coming in. So we have now the molar flow rate of H2O on the reactant side times the enthalpy of formation for H2O. And that'll be the molar value. And so that takes care of the first part of the right-hand side. But now we have to go back, and for all of the terms on the products, we're going to have to flip the sign. So we will now be subtracting off. And the first thing we'll have is now the molar flow rate of the water in the product side. Now we've separated the enthalpy out, so that stayed on the left-hand side. So now we just have the enthalpy of formation and the enthalpy of the reference. And so we'll do enthalpy of formation minus the enthalpy of the reference state, and we'll note that this is for water. And so that was the first term. We can now go ahead and do the second term, N dot CO2. And again, same setup. We're going to have the enthalpy of formation minus the enthalpy of the reference state. and this is going to be for carbon dioxide. So that is the first two terms. Now minus, we'll have the molar flow rate of the nitrogen, N2. And we're going to put parentheses because it's going to be a minus href. To the reference enthalpy, because there's no enthalpy of formation, we've separated this out. And so technically we could do the minus, a minus, bring that to be a plus. I'm going to leave it like this for now. And then we can do the same thing for oxygen. So N.O2, so have the same setup of the reference. And we'll note that is O2, and this one was N2. Okay, so we have the equation written like this. Now, why do we want it written like this? Let's just take a look here. So on the left-hand side, we have some mole flow rates, and we have some enthalpies. And so all of these enthalpies, this enthalpy here, this enthalpy here, this enthalpy here, this enthalpy here, this is just going to be a function of T2, where we'll call T2 the temperature of the products. So that's what we're going to need to find. We need to find the temperature of the products. This contains all of that information. It's got all of the temperature of the product terms that we need, but it's still distributed over all of the species that are in the product. But again, this is what we're going to be looking for. In terms of the right-hand side of the equation, everything here is known. So we have the enthalpy of formation. We have an enthalpy of formation. We have an enthalpy of formation. Enthalpy of formation, that should be a molar enthalpy. So those are things that we can easily go look up. I'll put that in black here. And the other thing that we're going to have is an enthalpy of a reference state, enthalpy of a reference state, enthalpy of a reference state, enthalpy of reference state. All of those things are things that we already know. And so from this, we basically have everything. We can calculate the right-hand side just by doing a lookup, but the left-hand side is going to be where we have to put in a little bit more work. And so I'm just going to go ahead and show what I'm going to do here. And so the left-hand side is what I'm going to call left-hand side for a variable. This has to equal the right-hand side of the equation. So this is basically what we're going to do. We're trying to set this up so we can take a look at these two different parts and compare them. Now, the first thing that we'll want to do, once we realize that we're going to have to do this comparison, we're trying to solve for this temperature, is to take a look at the right-hand side first, because again, we know everything we need to make that calculation. And so we have to look up some values. And so in terms of the lookup, we are going to need the reference enthalpy in kilojoule per k-mole. And we're also going to need the enthalpy of formation. And this is also going to be a kilojoule per k-mole. So those are going to be the two things that we need to go find in our tables. Now, I'm going to go ahead and just get these pieces of information down. We're going to first start with our fuel. And so I'm going to see if I can scroll up. Actually, that might work. Okay, so in terms of the fuel, the only thing that we needed was the enthalpy of formation. We don't need to worry about the reference state. So I'll just put an X there for now. And so the enthalpy of formation, if we go ahead and do this, it's a minus 208,450 kilojoules per k-mole. So that is the first thing that we needed to look up. Second thing, I'm going to go ahead and just do this in order of the way that it's going to be in the textbook. So next thing that we'd want to look up is for nitrogen. So nitrogen, we are going to need the reference state. And so we can go ahead and do that. H reference for nitrogen is going to be 8,669. And then the enthalpy of formation is 0 for nitrogen. The next part of the table we'd want to do, it'd be our oxygen. Oxygen is going to have a enthalpy at the reference point of 8,682. And it also has an enthalpy of formation of 0. We already made that note. Okay. And then we'll still need to do our water and carbon dioxide. So if we go look up water, it will have a reference value of 9,904. And it's going to have an enthalpy of formation of minus 200,041, 820. So yeah, 241,820 is the value there. And then lastly, we can do our carbon dioxide. Carbon dioxide at the reference date, 9,364. And the value for the enthalpy of formation is going to be a 393,520 kilojoule per kmol. Okay. So those are the reference values that we want to look up. And so once we have all of these values, we said we can now use these to calculate the right-hand side of the equation. Now, when I say right-hand side of the equation, I mean all of this from the fuel, the water here, we have the carbon dioxide, we have the nitrogen, we have the oxygen. Everything in here is now something we can calculate. And so let's go ahead and do that. So plugging these values into Excel, we can get the right-hand side of the equation. And so just to show the equation here, we plugged in what we've known. We've used the mole flow rates. We're going to do this per kmol of fuel. So we plugged in 1 for the fuel. Everything else just becomes the stoichiometric balance that we had in the first part. And so again, when we do that, we get this value for the right-hand side, which is going to be quite large. And so let's go ahead and set this up. So we have the right-hand side. The value for this was going to be 585.7029. This will be kilojoules. So that gives us the right-hand side of the equation. And so we have half of it now calculated. We still have half of the problem still to go, because we know that, again, left-hand side, which is going to be our function of temperature. So we'll note that this is what we need, function of the pressure or temperature of the products. This has to equal now the right-hand side. And so now we're going to try and use that right-hand side to help us figure out what is the temperature of the product. Now, we already wrote out what the left-hand side is. It's just going to be the molar flow rates times the enthalpy for each of the different components. But each of these components has got different enthalpies. And so question we have to ask ourselves is, where do we even begin to start this iterative process to actually be able to make this calculation? And so what we're going to do is we said, well, we needed to figure out where to start. And the best way to do that is just so we'll just say guess 1. So our first guess that we're going to do is we're going to assume that all products are going to be nitrogen. And so once we can assume that, that means that all of the enthalpies that we have are just going to be the nitrogen enthalpy. And once we can figure out that value, we will have what the temperature of the products is, kind of a guess value. And so how do we go about implementing this? Because it's easy enough to say, okay, all of them are nitrogen, but what does that mean in terms of setting this up mathematically? Well, we're going to go back up to this equation, and what we're going to say is all of the enthalpies that we have, so the enthalpy of H2O, enthalpy of CO2, enthalpy of nitrogen, enthalpy of oxygen, all of the enthalpies are now equal to nitrogen. And so in terms of rewriting that equation, that left-hand side, well, we can simplify this down. It becomes first the mole flow rate of the water on the production side, plus the mole flow rate of carbon dioxide on the production side, plus the mole flow rate of the nitrogen on the product side. And then we have the mole flow rate of the oxygen on the product side. And we can move all of those inside. So we just sum up all of the mole flow rates. And we're then able to multiply that now by the enthalpy of nitrogen for our product. And so again, all we've done is we've just said all enthalpies are that of nitrogen. So that is the main assumption. Now, just to finish this equation, we know the left-hand side has to equal the right-hand side of the equation, which we just calculated. So we have the right-hand side. And so if we go back and check, we should be able to do this because we know what is the mole flow rate of water. This would be 10.48. We should know the molar flow rate of CO2. This would be 8. We should have the molar flow rate of nitrogen. This should be 61.1. And for oxygen, this should be 3.75. All of those are in kmol. And so if we go ahead and bring all of this together, we'll find is we'll have 83.33 kmol. And this is then going to be multiplied by the enthalpy of nitrogen on the product side. This has to equal the right-hand side. This is the only thing that's unknown, the enthalpy of the nitrogen. And so if we go ahead and solve now for the enthalpy of nitrogen on the product side, this is going to equal 70,287, and just for good measure, 0.2 kilojoule per kmol. And so we have now the enthalpy of the nitrogen at the exit. Now, if we take this value, we can say, well, enthalpy for an ideal gas, only a function of temperature. And so this means we can now do some linear interpolation to get the temperature of the product. And doing a little bit of rounding, we'll find that the value for our first estimate should be about 2,150 Kelvin. And so this will be kind of the starting point for our estimate of the final temperature. Now, this estimate is going to be an overestimate. Now, why is it an overestimate of T sub P? Well, we know nitrogen, again, accounts for most of the mass in the system. It's probably 70 to 80% or more in most cases. So in terms of the enthalpies, if we look at the values, well, the enthalpy for nitrogen, even at the reference state, is going to be the lowest of all of the ones that we have. And so the enthalpy of water and CO2 are going to be larger. And while these will account for only a small amount of the overall mass, replacing the enthalpy of the water and the enthalpy of the CO2 with this nitrogen enthalpy results in an underestimate, or it's an underestimate of the enthalpy at the state, which means that we're going to overestimate the temperature. And so that's kind of the reasoning behind it. I don't want to go ahead and show like the exact, numbers at like a high state. We'll kind of see that as we start to get into the guesses. We'll see that the enthalpy for oxygen and nitrogen are going to be significantly smaller than CO2 and water at the higher temperatures. So this difference becomes much more of an effect. And so we'll see that as we work through kind of the examples here. So now that we have this value, what do we want to do to actually solve this problem? And the answer is we need to probably pull the temperature down because we know it's an overestimate, and then just choose a value, guess, compare the numbers, and see what happens is kind of the short answer on how we're going to do this. And so what I'm going to say is for the first part, let's go ahead and guess that the temperature of the products is going to be, let's say 150 K less. So we'll say that it's an even 2000 Kelvin. So nice round number to begin. It's a little bit lower because it's an overestimate of the value. And we said, okay, let's go to the back of the textbook and do some lookups. So at this temperature, we can get the enthalpy of the oxygen. This is going to be 6,800, or sorry, 6,007, not 600, 67,881 kilojoule per kmol. We can get the enthalpy for the nitrogen. It's going to be 64,810 kilojoule per kmol. We can get the enthalpy for the water. The enthalpy for the water is going to equal 82,593 kilojoule per kmol. And then the enthalpy for the carbon dioxide, this is going to equal 100,804. And all of these have the units of a kilojoule per kmol. And so what I was just saying before is we can see that the enthalpy of water, enthalpy of carbon dioxide are going to be much, much larger than the enthalpy of the nitrogen. And so it's going to scale a little. This is going to have a more important effect, particularly at higher temperature, at basically bringing down that estimate. And so that's, again, why we overestimated it just with nitrogen. Okay. And so if we go ahead and combine all of these numbers, we can use the equation that we developed back here, where we have now the mole flow rates times each of their corresponding enthalpies, and we can now guess the left-hand side of the equation. And so what we're going to do here is we're going to solve for the variables on the left-hand side. And so if we go ahead and pull this up, so here is the equation. We're going to note that this will be the enthalpy at 2000. So we have that value. Now rather than watch me retype them, I already have those numbers saved here. So just let me put those in. And so if we put these numbers in, we should be able to calculate our left-hand side of the equation. So left-hand side of the equation is going to be that same setup that we just had in terms of the equation on the sheet. So we've went ahead and done that in Excel. And then what we want to do is we want to calculate the difference between these two. So let's first get the left-hand side of the equation in here. So we have the number right here. I'm going to go ahead and just write that down. So for this first guess, the left-hand side of the equation is going to be 588,645,1. And so that should give us the value that we need. We'll note that this is a kilojoule. And so we now have a value for the left-hand side of the equation. We have a value for the right-hand side of the equation. We want those two to compare. And so because we're going to make a comparison, we're figuring out how well our estimate is doing. We're going to take the left-hand side of the equation, and we'll note that this is our first guess, so left-hand side 1. So left-hand side 1 minus the right-hand side of the equation, and this is going to give us some number. Now, because this is a guess, we're not going to have these match perfectly, so I'm going to call this value the coefficient number 1. And coefficient number 1, when we do these calculations, well, I have it here in Excel, that would be this value right here, which would be the left-hand side minus that right-hand side calculation. And so we can go ahead and put that into the number for C1. And so the value for that was 29422.1 kilojoules. And so that's the difference now between our guessed value that we did for the left-hand side and our known value on the right-hand side. Now, ideal world, we want this to equal 0, so the left-hand side should equal the right-hand side. This is what we want. This is what we got. We have a value that is going to be greater than 0. And so we'll note that C1 is greater than 0, which means that the left-hand side was too large. And so if the left-hand side is too large, that means that we overestimated the temperature. Which means, again, we're still too large. We need to reduce our guess temperature to see if we can get a little bit closer. So again, just doing it this way, C1 just means that we have too much energy on the product side right now because the temperature is going to be too high, and so we need to go back and rethink the guess value. Now what we can do is we can take a look at the tables and try again. And so this was a little bit too high. So let's go ahead and for our second guess, we will reduce the temperature of the product. So the temperature of the product will now be 1980 Kelvin. So to decrease it by about 20 degrees K, or the same thing as 20 degrees Celsius. And we'll run the tabled values again. And so in terms of our guess, we'll guess the enthalpy of oxygen. We'll go look this value up. This will be 67127. We can guess the value for, or not guess, we can look up the value for nitrogen. This is going to be 6,490. Actually 64,090, sorry. We can get the enthalpy for the water at this state. It's going to equal 81,573. And we can now get the enthalpy for carbon dioxide. This value is going to be 99,606. All units are going to be a kilojoule per k-mole. And so once we get these values, we can go ahead and calculate the left-hand side for the second time. So left-hand side, number 2. And I'm going to go ahead and show that we have a value. So I know the value is going to equal 5819358. And this is going to be a kilojoule. And so let's go ahead and run this calculation. So I'm going to go ahead and put these numbers in. And so we can say that we know that this is going to be the enthalpy at 1980 for our temperature. So we have all of these enthalpy values. We need to calculate the left-hand side. So we can just go ahead and drag this over. And so this will be our new left-hand side, accounting for the new input values, which means now we have to recalculate the left-hand side minus the right-hand side. So we'll go ahead and reset this. And so left-hand side minus the right-hand side. We now get our coefficient, which will be C2. We see that that value is going to be a negative number. So let's go ahead and add this into our Word document here. So we have now the left-hand side 2 minus the right-hand side. This is going to give us the coefficient C2. C2 is going to be a minus 37671.03 kilojoules. And so we see that this value has a negative sign. So we can say C2 is going to be less than 0. So this is now going to be an underestimate, which means that the temperature is now going to be too low in terms of the final product. So that means that the enthalpy, the energy that's at the final state, is not going to be enough. And so we have to go back and we have to rethink what is that value going to be. Now what we could do is we said, well, this is going to be somewhere between 1980 and 2000 Kelvin. There might not be the absolute value in the textbook. And so what we could do is we could, for every value, so enthalpy of O2, nitrogen, oxygen, water vapor, CO2, we could do some linear interpolation between all of those. But that doesn't really sound like fun, because we know that this is all just going to be a linear interpolated value from the table. We said, well, we could just do one linear interpolation at this point. We have a bounding value that's too high. We have a bounding value that's going to be too low. So let's go ahead and just use the results that we just got to try and figure out what that temperature is going to be. And so what we're going to do is we're going to do a linear interpolation using our coefficients and our temperatures. And so what we mean by that is if we want to do linear interpolation, we have a set form. And so the form that I always like to do is if we're looking for something, and so we're looking for the temperature of the product. This is going to be related to the change that we'd have. So this would be the temperature of the product for guess 1 minus the temperature of the product for guess 2 over the coefficient C1 minus the coefficient of C2, now multiplied by the value that we want for our final state for our coefficient. Now, if we go back up, we said the final value for the coefficient that we want is going to be 0. And so we're looking for the case where the coefficient equals 0. And then we can just add in minus C2. And then that will give us the linear interpolated result. Then we just have to add in our base temperature, which was the low side, so it would be 1980. And so this will be Kelvin. And so this will now let us solve for the final temperature of the product. And so at this point, let's go ahead and do that in Excel. So the final temperature, well, we said this was going to equal our starting value for a temperature. So that was going to be our initial guess, which was 2000 Kelvin, minus 1980 for our second guess. Now we have to divide by the difference between our coefficients, so C1 minus the coefficient C2. Now this gets multiplied by 0 minus the coefficient C2, parenthesis, plus the low side temperature, 1980, and we should get our final temperature. We see that was almost perfectly halfway between our two guesses. The final temperature is 1991.2 Kelvin. So the final value temperature of the products will be 1991.2 Kelvin. And if we wanted to go ahead and convert that to Celsius, this would be 1718.2 Kelvin. And so there we go. We've gone through the calculations. We figured out what is the adiabatic flame temperature for this problem. Now, what I want to suggest is when you do this on the homework problem, you do use Excel. You're going to have to probably guess and check a few times. Using Excel will make your life a little bit easier whenever you have to do some sort of iteration, which is necessary for these adiabatic flame temperatures. So make use of the Excel. It will make your life easier for these calculations. Now, the few things that did I calculate C2 wrong? There's
just in your final answer. So you wrote K, that should be degree C, right?
Oh, yeah. Sorry. I thought you meant the coefficient. Yeah, sorry. That should have been Celsius. I was thinking Kelvin because that's what we've been doing up to that point. Yeah. But yeah, we have Celsius. Thank you for that. Okay, so the one thing I do want to note when it comes to adiabatic flame temperatures is there are ways that we can, of course, increase it. This is based on the given problem statement. If we want to increase the adiabatic flame temperature, we can bring in the air and the fuel at a higher temperature. So if you were doing combustion and you wanted to get a little bit hotter fluid, you just kind of preheat the air before it comes in. The air comes in with more energy, therefore your final state can be a higher energy state. That means you have a higher flame temperature. It's also going to depend on your composition of your combustion reaction. So if you bring in excess air, that's going to decrease your flame temperature. If you wanted to use pure oxygen, that would increase your flame temperature. If you had a perfectly balanced stoichiometric equation, that will be better than having any sort of excess oxygen that will be in the products. And so there's a number of things that can change this answer. It will depend on what you bring in, but in this case, given the bounds that we had for our stoichiometric setup, this would be the maximum temperature that we would expect the products to ever have. But realistically, we are going to lose some heat out the sides. And so again, this represents kind of the mathematical maximum temperature for combustion. And so that is the adiabatic flame temperature. Okay, so that will wrap up this example problem. I know this is a very long example problem, but I do want to show how you do the iterative solution. And at this point, I want to transition back into the PowerPoints that we had from last Friday, and we were going to finalize the last few things where I can make some kind of final comments on combustion. And so what we want to say is everything that we've done, all of the stoichiometric balances that we've seen is going to be kind of a simplification. So what we've considered is only what we consider is the global reaction. And we've only done that for complete combustion, which means that in terms of what's actually going on, it's kind of hidden from us. And so what we mean by the global reaction is where we have air, fuel, that goes into our water, that goes into carbon dioxide, and then nitrogen and oxygen. And that is true of only perfect combustion, perfectly complete. Now, the real truth of this and what's hidden from you is the fact that that reaction doesn't just happen. You don't have the air and the fuel just go into a container. All of a sudden, all of the molecules split down to their base atoms and then get reconfigured into carbon dioxide and water with some nitrogen and oxygen. That's not how it actually works. What happens is you start with your fuel molecule. Your first reaction will take off a molecule or two, depending on the structure, and then you start breaking away all of the individual bonds of your fuel, and you have many intermediate reactions that have to occur. So your fuel has to break down in steps, and that slowly gets converted into your water, into your carbon dioxide as it goes through the system. And so an example that we could see is methane. It's a pretty simple fuel structure that could have up to 350 different reactions with over 53 different individual chemical species that need to be accounted for at any given point. Now that would be considered on the simpler side. If you looked at jet fuel, you're going to have like 221 was a value I found in literature for the number of different chemical species that you could have. And you could see over 5,000 different reactions happening inside of your system. And so this problem gets complex very quickly to actually consider what's going on inside of the system. It's very, very intricate. But I wanted to tell you what it is so you at least could see where if you wanted to go into combustion, you wanted more details, what's going on. And so what the simplest way to kind of phrase this is for every reaction that we're going to have to consider, well, we would have to also consider what's going on, what's the rate that that's happening. And you probably saw this in chemistry. And so you have a reaction going here. So we'd have H2 plus O2 goes to the products of HO2 plus H. And so you could have the forward reaction, which would be the forward value 1, and you could also have a reverse value of this reaction. And now we could do this for multiple different setups. So that'd be forward 2, this would be reverse 2. We could do this for K forward 3, K reverse 3, and we start to see that there's this pattern. So we have all of these different reactions going on, and so all of these technically could be like present in a system. Now, why is this going to be important? Well, because we have to now go through intermediate reactions, we can see that if we wanted to track the amount of oxygen, O2, that we have in the system, well, we want to know what's happening, how many moles of oxygen do we have at any given point. And so that value will now vary with time. So it's no longer going to be just a static problem. It's going to be a dynamic problem in terms of figuring out concentration. And so to figure out the concentration of O2 in our system, we have to figure out how is it changing. And so we have to do this per unit time. So this would figure out how O2, the amount of oxygen, is changing with respect to time. And we'd have to first consider how much oxygen is being created. And so for the creation of oxygen, I'm going to go ahead and erase these so we can see what's going on. Well, we could have some of the products here going in the reverse reaction, creating O2. We could have the same thing down here going in the reverse direction, creating O2. And so we'd have the reverse coefficient from 1, we'd have the reverse coefficient of 2, creating oxygen. And then we could also have oxygen being destroyed, which would be the forward reaction of both of these. So we have the forward reaction and the forward reaction. based on the content. And so now we have to figure out how does the concentration of each of our individual species change with time. Now, why is this important? Well, we can't have one reaction happen until we might have enough oxygen. So if we were to look at the creation of maybe water, so let's use water as the example, well, we need to first have some OH present, some H2 present. And so that's going to depend on these intermediate reactions. So the reaction that we need to get OH, which would be here, has to depend on the formation of hydrogen plus oxygen. And so the single hydrogen molecule, well, that comes from this reaction up here. And so we first have to form the monatomic hydrogen to then form our OH to then be able to get to this reaction. And so certain reactions can't happen until certain chemicals have been formed or certain molecule or atomic structures have been created. And so this is why it becomes a time-dependent process. You have to wait for a certain element to be present before the next reaction can occur. Now this gets to be incredibly complicated and there gets to be a lot going on. Yes, they're very fast, but because you have to wait and go through these step-by-step processes, well, combustion now takes time to complete. And we actually saw this when we did the second lab, which was the CFR engine lab. We had to pre-ignite the fuel so that the combustion had just enough time to break down the molecule so that we could start to see the more complete combustion by the time we reach top dead center position. And so that is why this becomes a much more complicated problem, is because now you have to do chemistry, but you have to do it in the right form. You have to keep track of all of these different reactions. And so you can have many different species, many different reactions. You're going to need a huge system of equations to be able to get into the details. Now, a brief overview of this is what we can see is for methane. We can bring our methane fuel in, we start breaking it down by chemical structure, and it becomes kind of a branching tree diagram, and we have to work through as we start breaking down the fuel molecule. So first thing we do is we take off a little bit, one of the hydrogen molecules, and then we have all of these chemical reactions that have to happen. But by the end, we'll form carbon monoxide, which then gives way to carbon dioxide, which is the final step in the process. Now, in terms of trying to figure out what's going on, that's what this bottom figure is supposed to show. This is basically, it's the distance from the injection point, but if we think of this as kind of a steady state kind of open system, the distance from the injection point, that's basically the time that it's taken for combustion. And so what we see, and this is from a different fuel, I didn't have a matching figure for methane, is that if we bring our fuel in, we see that the amount of the fuel over time is going to decrease as we start breaking down the chemical structure. We start to see some of the intermediate fuel molecules increase as the initial fuel molecule is broken down. And as it progresses, we'll eventually see a big spike in the carbon monoxide. So this is the peaking of the carbon monoxide, indicating we've gotten most of the way through the combustion process. And once we start to have a lot of carbon monoxide form, that will then give way to the final step, which is going to be the creation of carbon dioxide. And so here we have carbon dioxide. We see that's the last step of the process is the carbon monoxide starts to decrease, the carbon dioxide increases. Now for complete combustion, we need all of the carbon monoxide or most of the carbon monoxide to give way to carbon dioxide because that's the last state. Now this is why carbon monoxide is going to be present. So we have to take into account now the equilibrium chemistry, and so there will be some carbon monoxide present for any combustion. But why we also don't consider it is to figure out how much carbon monoxide we'd have. We'd have to figure out how complete of a reaction did we have happen, and to do that we have to do all of the intermediate calculations. And so this is kind of the complex nature of combustion. Now, one thing I do want to point out is if we look at the temperature of the system, we can see that the temperature only begins to increase once we start forming the amount of carbon dioxide. So the formation of carbon dioxide is going to release a lot of energy, which is why it's also very important that we don't keep a lot of carbon monoxide because we're not having that complete combustion. We're not getting all of the heat that we could get out, and that comes from the carbon dioxide forming from carbon monoxide. And like I said, there's a lot of intermediate chemistry. I wanted to very briefly introduce you to what's going on in terms of those reactions. This is not on the exam, but what happens is if you consider the system, how do you figure out where there's equilibrium? Well, we'd have to look at the entropy because entropy always has to increase. And so the equilibrium composition will always happen at the point of maximum entropy, which means that if we do a whole bunch of stuff that we can combine, we can create something called the Gibbs function. The Gibbs function is basically like exergy, where it's a combination of enthalpy and entropy. Should be a large S. And what that means is all reactions are going to tend towards the point. If we look at how we've set this up, Gibbs must always decrease. And so it will always tend towards the minimum value for the Gibbs function. And that means that the equilibrium state will be defined by a change in the Gibbs function equaling 0 at the inflection point. From this is where we get into a lot of chemistry. And so you can set up these reactions. You can now take into account the Gibbs function for a value. You can relate this to how the Gibbs function will change for this chemical reaction. It will give you this setup. You'll note that this setup is the same thing for an ideal gas to figure out the rate equation. And so the rate equation is now a function of the Gibbs energy, or a Gibbs function, which again is related to the enthalpy and entropy. And so the rate constant for any reaction is now going to be a function of the thermodynamic properties. And so how we create that or destroy an element is now related to the actual state of the element. And so once we bring that back into this, well, not only do you now have all of these intermediate reactions, but you now have to figure out what the state for those reactions are occurring, because that will now give you the constant, and the constant for any of those reactions depends on some thermodynamic properties. And so that is a brief introduction to why we stop where we do when it comes to combustion. It's because this problem snowballs very quickly, but it's a very important and very kind of detailed topic. So if you are interested in combustion, I wanted to give you an idea of what goes beyond what we talk about here in this class, and kind of give you a reason to why we stop talking about chemical reactions when we do, because the issue snowballs very, very quickly. Okay, so that is where we're going to end today's lecture. I just want to point out that these last few slides with the concluding remarks, this was meant for you to just kind of have an idea of where we were going, what's next. You don't have to know how to do all of this chemical reaction information with the reaction coefficients. This is just kind of looking forward to, again, beyond what we'll talk about in this class. Okay, if you do have any questions, let me know. Otherwise, that will be the end of the content that we'll cover. Just a reminder again, this week in lab, make sure you come prepared for exam number 2. Otherwise, that is where we're going to end today. I hope you guys have a good rest of your evening. Make sure you get the homework completed. Make sure you study. And if you have any questions, let me know. Otherwise, that is the end of today's lecture.